So we will start today with a new chapter, which is chapter 90. In this chapter, we'll introduce the linear and angular momentum and the principle of impulse and momentum. So we have already studied previously the application of impulse and momentum, linear impulse and momentum on a particle. Now we'll move to a rigid body. So whenever we talk about, and we also introduced before also angular momentum when we talk about a particle. Now we'll move to analysis with a rigid body. So we will consider in this chapter how to apply these theorems, okay? And how sometimes we can solve in an easier way using the principle of impulse and momentum. So in this chapter, we'll be able to develop formulations for the linear and angular momentum of a rigid body, and we will apply the principle of linear and angular impulse and momentum. So to start with, we know that the linear momentum of a rigid body is defined as L equals to mvg. So when we considered a particle, the difference is that for a particle, we just have one point. So the linear momentum is mass times velocity vector. Now, what is new is that for the rigid body, you have infinity of points on the rigid body that you can represent by which is the center of mass. Okay? So since the center of mass will be a representative point for the body, then the linear momentum of a rigid body can be simply calculated as the mass of the rigid body times the velocity of its center of mass. And this equation will state that the linear momentum vector L has a magnitude equal to mvg and a direction defined by vg vector. Now, what about the angular momentum of a rigid body? The angular momentum of a rigid body about a certain, we'll learn to find it about any point. But in particular, if you want to find it about the center of mass, the angular momentum of a rigid body about the center of mass is the inertia about g times the angular velocity omega. And remember always that the direction of AG is equal to the direction of omega, so it's perpendicular to the plane of rotation. Now, in order to derive, if you want, the principle of angular momentum for a rigid body, and in order to know how to calculate the angular momentum, we need to go back to physics. Yani if we want to consider angular momentum about any point, not about g. If you are interested to find this angular momentum about any point in space, we need to develop a technique to do it, okay? We know that for a particle, if you have a particle, the angular momentum of a particle about a point P is simply R, position vector R, vectorial linear momentum. So by definition, the angular momentum of a particle, as we know, is the moment of the linear momentum about any point, about the point of interest. So if you want to find the angular momentum about P, you need to consider vector position from P to the point, okay? And this is vector R. And then you consider your vector MV. So you do R vectorial or cross product MV. So this will give you the linear momentum of the angular momentum of the particle about point P. Now, a rigid body is an infinity of particles. So we have several small elements. If we consider elementary mass dm, okay? This elementary mass dm has a linear momentum. The linear momentum of this elementary mass, if this mass is I, so this is dmi, okay? And then the linear momentum vector is dmi times VI. And we know that the angular momentum of this particle is simply h of about p of particle I is equal to the position vector from the point about it I am doing the angular momentum to the point of interest, to I. So it's vector here, if you want, if we call this point A, vector R is PA. So vector R represents the position vector from the origin, P, or from the point about it we are doing the angular momentum, to point A where the particle is. So this is the position vector R. So HPI is just R vectorial, the elementary mass of the particle, times VI. Now, to continue, okay, we need to integrate, to find the angular momentum. This is elementary angular momentum. To find the angular momentum over the whole body, we need to integrate this. We need to perform integral procedure. Okay, and in order to come up, if you want, with a general expression for the angular momentum, we'll find an expression of VI, which is the velocity of the elementary mass, function of the velocity of point P. So since point I, which is any point on the rigid body, and P are both attached to the rigid body, their velocities can be related by the following formula. So VI is velocity of point P plus velocity of I relative to P. And we know that VI relative to P, when the 2 points are attached to the rigid body, and we consider it translating frame at origin P, the relative motion of I with respect to P is rotation, because the distance between P and I is fixed. So the relative velocity between the two is omega of the rigid body vectorial R. So now we can replace in the angular momentum of the particle, we can replace VI by its expression, by Vp plus omega vectorial R. And then we decompose Vp into Vpxi plus Vpyj. We know that in 2D motion, omega will be perpendicular to the plane of motion. So if the plane of motion is xy, omega will be along k. And for the position vector, it's an arbitrary position vector. So its the coordinates of this position vector are xi plus yj. Now, if you apply the cross product on this term, and you just have to expand, okay? If you do expansion, you know that I vectorial I is 0, okay? J vectorial J is 0, I vectorial J is plus K, etc. You expand these terms and you end up with the following result. And we know that the angular momentum is along K. Yeah, HP will only be along K, and you can verify this because when you do the cross product, you will have from the other side only K terms, okay? So we can find that HP of any particle I can be written as minus the mass of this particle y Vpx plus mass times x Vpy plus mi omega r squared. This is the elementary angular momentum of one particle, but you need to determine the total angular momentum. To get the total angular momentum, we will integrate over the rigid body. So if I integrate over the rigid body, I will find a simplified expression for the angular momentum about P. So the angular momentum about P after integration will be given by the following expression. First, when you integrate your terms, okay, you have several terms that are mathematically, and you can replace them by mathematical expression. And if we talk first about integral y dm, you know that integral y dm can be replaced by y bar, which is the coordinate of center of mass, times the total mass, times Vpx. Now, for the second integral, integral x dm can be replaced by x bar times total mass. And integral r squared dm is what? Do you remember what is this term? This is inertia. This is the inertia, okay, about point P. So this is how we can calculate the angular momentum about any point P on the rigid body. It's equal to minus y bar mvpx plus x bar mvpy plus inertia about P times omega. Now, in case the first particular application of this formula is to consider that we will put P on G. So if I put P on G, what will be X bar and Y bar?
Zero.
Zero. So these two terms will cancel out, and I say that angular momentum about G is Ig omega. Okay? So this is the first application of this formula. Another application is if you consider rotation about fixed axis. So consider that we have rotation about P. If you have rotation about P, this means that P is fixed. If P is fixed, so Vp is 0. So in case you have rotation about fixed axis, Vp will be 0. So Vpx equals 0, Vpy equals 0. Then in this case, you can say for rotation about fixed axis passing by point P, Hp can be written as inertia about P times omega. Please pay attention, only applicable if P has a velocity of 0. And if P is an instantaneous center of rotation, or or we have rotation about fixed axis passing by P, then we can apply that the angular momentum about this point is inertia about this point times omega. For point G, it's always applicable, whatever is the type of motion. If it's translation, rotation, or general plane motion, you can write that the angular momentum about G of the rigid body is equal to Ig omega. While this one is only applicable in two cases, if P is IC or we are rotating about P. So if P is IC or on axis of rotation or on axis of rotation. Okay. So now that we defined how to calculate the angular momentum for a rigid body, we can proceed. Okay. So here they are demonstrating what we were talking about. Okay. Now, you can also demonstrate another expression for angular momentum about P. So if P is an arbitrary point, you can say that HP is obtained from the previous general expression here, but also you can express HP function of the velocity at the center of mass. If you want to do this, you need to relate Vpx, Vpy to Vgx, Vgy. How we can do this? We can say that P and G are 2 points of the same rigid body. So we can correlate the velocities of point G and P by writing Vg equal Vp plus omega vectorial Pg, okay, which is vector R bar. So we can replace R bar by X bar I plus Y bar J. If we do this, okay, if we replace Vpx, Vpy by their expressions, function of Vgx, Vgy, will end up with the following relation. So first, from here, we can get an expression for Vpx, Vpy, function of Vgx, Vgy, replacing them in our equation here. We can demonstrate that HP can be written as minus y bar mvgx plus x bar mvgy plus igwy, because look, if you use the parallel axis theorem, here you have, in the previous equation, okay, you have, you replace VPX and VPY by their expression. And what is IP actually? IP is the inertia about P, but you can relate inertia about P and inertia about G using which theorem?
Parallel axis.
Exactly,
Parallel
parallel
axis
axis theorem. So you can replace IP by IG plus mass of the body times distance square between P and G. The distance between P and G is x bar square plus y bar square, okay? So if you replace IP by this expression and you replace VP x, VPY by their expressions function of VGX, VGY, you will see that these terms will be simplified, okay? Because look, you have here you can replace VPX from this equation, can be VPX is VGX plus y bar omega. Okay. So if you replace here, if you replace VPX by its expression, okay, in the equation, you will obtain here, you will obtain y bar m times minus, so instead of VPX, you can write the expression. لحظة, I think here they should put okay, they did it in the opposite way here. 1 second. You should replace here in this equation, in this general equation, okay? So in this equation, if you replace VPX by its expression, okay, and you replace VPY by its expression and IP by IG mx bar square plus y bar square, I will notate it here for you to see it, okay? So I will take these equations here. So minus y bar mVPX plus x bar mVPY, let us write it. So HP is equal to minus y bar m VPX. Okay, look, instead of replacing directly VPX by its expression, you know what they did? They kept VPX, okay? They kept VPX as it is, but they said, no, here we replaced IP W, we replaced it by IGW, okay, plus the mass times x bar square, okay, plus y bar square. And now what they did is that they considered, since also here we have m y bar times m in this expression, they said, why to not take this term into factor with it? And if you consider that here from this expression you have mx bar square plus my bar square, okay? So if you take this term now, you can write it as my bar times y bar. So instead of replacing VPX, if you want, by its expression, they just considered, I take a y bar m in factor. What do I get? I get inside minus VPX plus y bar omega. But according to my relation between VGX and VGY, VPX minus y bar omega is simply VGX. So now this term can be replaced by VGX. But if you use the other method, you'll get exactly the same result. And instead of taking, if you want, in factor y bar m, you can just replace VPX by its expression, and you will have minus y bar omega square plus m y bar square. They will cancel out. And both methods will lead to the same result. But here, instead of replacing VP by its expression function of VG, they try to appear VGX in the equation. Okay, so by taking this term with this one, they can replace this whole term by VGX. This is what they did. Okay, but if they didn't do this, you can replace VPX from this equation. You can say, I can replace in my equation VPX by VGX plus y bar omega. Okay, and if you do this, going back to your equation, you have that the angular momentum is equal to minus y bar m VPX plus x bar m VPY. Okay, and instead of IP omega, as we said, you can replace by IG omega plus mx bar square plus my bar square. Okay, so we can say, let us replace VPX, for example, by its expression and VPY by its expression. If you replace VPX by its expression, you will have, instead of it, VGX plus y bar omega. So you will get minus y bar m times VGX. Now you have minus y bar m times y bar omega. So minus y bar square times m times omega. Okay. So as you can see here, you will have the following two terms. And here you have minus y bar square m omega. Here you have plus my bar square omega. These two terms will cancel out. The same will apply for the term mx bar square omega. You will have from the other side minus mx bar square omega. They will cancel out. So you will end up with a simplified form, okay, which is minus y bar mvgx plus x bar mvgy plus ig omega. So to reach this, or you replace VPX, VPY bar their expressions, or you try to appear the terms VGX, VGY as they did here. So, and to know what is VGX, VGY, you relate the velocity of G and P as 2 points of the rigid body. So both methods will let you reach this equation, okay? So this is another way to calculate the angular momentum of a rigid body about a point P. It's equal to minus y bar mvgx plus x bar mvgy plus ig omega. This is the most general form, okay? Now we can take particular cases. The first particular case is if I take point P at G, so we'll go back to our previous result. Because if we put point P at G, what will happen? You will have y bar 0 and x bar 0. So we'll end up with hg equal ig omega. And if you consider, in case you consider a point that is fixed, okay? So if P is fixed and you want to find the angular momentum about it, also here you will go back to the previous result, which is the following. So if I consider that P is fixed, so what will happen? If P is fixed, G will rotate about P. So if I consider the terms VGX, VGY, okay? So let us consider that this is G. And you have VGX, VGY. So as I said in the figure, this is VGX, this is VGY, and this is vector MVG, okay? If you want to calculate, if you want to consider that P is fixed, if P is fixed, the velocity will not be like this. It should be perpendicular to PG. So your velocity vector will be perpendicular to PG. And what will be the magnitude of your velocity vector? The velocity of point G will be equal to
W times distance.
W times R, okay? So when you consider physically to understand the physics here, these terms actually represent what? When you do minus y bar mvgx plus x bar mvgy, can you tell me physically?
يعني المومنت تبع اللينير مومنتم
Very good.
around الجي.
Very good. Yes. This represents the moment of linear momentum about point P. Okay. This is the moment of linear momentum about P. To understand better this, look at the figure. Okay. What is my linear momentum? It's vector MV, MVG. And I will divide it into two components, MVGX and VGY. When I do, if you look at your figure, okay, if you consider the counterclockwise direction as positive, we have, this is vector. Let me change the color, 1 second. If you want to consider the moment of linear momentum and you decompose it into two components, MVGX and VGY. If you look at MVGX, it's rotating about P into the clockwise direction. So the moment is negative. So you can write minus MVGX. Now times the distance between point P and the line of action of VG. If you take the perpendicular, this is y bar. So times
Y bar.
Now, if you consider MVGY, the moment is counterclockwise, so it's positive. So plus MVGY times the distance, okay, between MVGY and P, which is x bar. So times x bar. So this term actually represents physically the moment of the linear momentum about point P. Okay, so in case P is fixed, what will happen? In case P is fixed, your vector MV will be perpendicular to the vector from P to G, because you will have rotation about fixed axis. Okay, and then you can say, in this case, how can I write the moment? The moment actually will be equal to MVG times distance d, and the distance d or radius of rotation is actually what? Is actually radical x bar square plus y bar square. So it's equal to MVG times radical x bar square plus y bar square, which is the radius of rotation. This represents the radius of rotation. So now if you replace a Vg by omega times r, what will be the value of your angular momentum? So the angular momentum then about G, okay, will be equal to m times omega times radius square plus Ig omega. Okay, and now if I take omega in factor, what do I get? I get
IP.
mr square, exactly, with r representing the distance from P to G. So mpg square plus ig. And actually this represent, if I use the parallel axis theorem, this term represent IP. So here again, I proved again that in case I have a fixed point, I have rotation about a fixed axis, or in case I have a point of zero velocity, I can apply about P, HP equals IP omega. Okay, so we were able to demonstrate again that if I consider a fixed point or a point with zero velocity, if it's the IC, then angular momentum about this point is inertia about this point times omega. And in case P is an
Doctor?
arbitrary point, all I have to do to calculate the angular momentum about this arbitrary point, I find the moment of linear momentum about P plus IG omega. Okay.
دكتور
Yes. Yes.
بس بدي أسأل لأنه شوي ضاعت بتاني كيس، يعني أول شي بس لقينا المومنت عزنا في جي إكس في جي واي،
Okay.
بس ليش بس اعتبرنا بي فيكست بوينت بس إنها في جي؟
اوكي، لانه بضل فينا نستعمل x و y. اوكي، بس انت if you know that you have rotation about fixed axis, you know the direction of your vector. يعني انت in which case you decompose into x and y. If you don't know the direction, you say I have two components, x and y. But if you know that you have rotation about fixed axis, you know that your vector vg in direction is perpendicular to pg. Okay, so you don't need here, Michelle, to decompose it because you know its direction. It's perpendicular to PG. So
Okay.
instead of decomposing the moment into two parts, you can directly say, what is the moment of MVG about P? It's MVG times what? Times the distance from P to G, which is the radius of rotation. Okay, so you can directly write
Okay,
instead,
thank you.
and until you do this division, if you don't know vector VG or you don't know the perpendicular distance from P to VG. But since you know here the direction of VG and you know the perpendicular distance, no need to decompose the moment into two parts. Okay.
Okay.
Other question on this?
يس دكتور
Yes.
اللينير مومنتوم ما كان
Yes.
فينا نحن نجيب المومنتوم العادي، اللينير مومنتوم العادي اللي هو ام في، نعمله تايمز الديستانس
أي عادي
ار.
يعني؟ What do you mean by linear momentum عادي؟
يعني بلا ما نقسم الفي على تو كومبوننتس بنجيب
البربنديكولر اكيد.
لا قبل
شو؟
عم بحكي بالفورمولا اللي قبل انه
اوكي
هيدي موا ايجريك بار ام في جي
اوكي
اكس بلس اكس بار.
صحيح.
ايه بلا ما نحط هود تو تيرمز ما فينا نعمل
بلا
ام تايمز
بلا
اي تايمز ار.
بس بدك تكون تعرف الديستنس. يعني انت اذا ما عندك روتيشن about
ايه
fixed
بس
axis،
مش ضروري التوتال مومنتوم اكتبه in form of vector يعني اي جي كي ما هيك
اذا if
انه
you are
بدنا
able, look,
value.
here is the idea. Okay, let us consider vector mvg for arbitrary motion. انت if you want to find the moment of this vector about point P, you need to know the distance from P to this vector. If you are able to calculate it geometrically, يعني in the geometry of the figure, it's easy to find. No need to decompose. Okay? And if you have this, if you know you
ايه
have
اوكي
arbitrary motion,
فهمت.
not rotation about fixed axis. You don't have rotation about fixed axis. Okay? And you want
اوكي
to
بس انا
consider
سؤالي
ايه
انه اتش بي لازم هي بدها تطلع سكيلر اما
هلا لانه
فيكتور
2
يعني.
دي، لانه 2 دي هون فيك تكتبها
مم.
مش vector، فيك تكتبها scalar لانه you will be sure that it's or in positive k or in negative k. You need to consider a positive direction and find just the algebraic value. Okay, بس in 3D
اوكي
in 3D مجبور تشتغل ب vectors because you will have three components I, J, K.
مم. اوكي
Okay.
يس ميرسي.
Other question? Okay. So now, if we consider let us start with particular cases. The case of translation is the easiest case. In translation, no omega. Omega is equal to 0. So we can say that the linear momentum is equal to mvg, and the angular momentum is 0, because what is the general formula for angular momentum about g? We said that hg, angular momentum about g, is equal to
IG omega.
ig omega. So since omega is 0, then it will simplify and hg is 0. But can we say that hp is 0 if I take any point p on the body? What will be hp?
No.
If you look at this figure, okay, you can say, what is the general formula for hp? It's moment of mvg about p, okay, plus what? Plus ig
IGW.
omega,
IG omega.
plus ig omega. So here no omega, this term will cancel out, but this term will not be 0, okay? What is the moment of mvg about p? Look at the figure here, it's very simple. You can say I draw the perpendicular from p to the line of mvg. I call this distance, for example, h, okay? And if I select the clockwise direction as positive, what will be hp? So here hp will be equal to
MVG
plus,
times small a.
exactly, plus mvg times small h, okay? So in translation, the angular momentum about g only is 0, but not about any point. Pay attention for this. Okay. So this is our first particular case. Now, if we consider rotation about fixed axis, okay? In this case, as we said, the point O has velocity of 0. And we have, for angular momentum, we have several options. We can use hg equal ig omega, but also, because this is always applicable, so it will be applicable in all cases. But in addition to this, we can write h about O equals, as we demonstrated together in previous slides, equals to io omega. Okay? And you can demonstrate this from the parallel axis theorem, and here they considered the demonstration for you. Okay? Now, if I consider any other points on the figure, I need to apply the general form. And if I consider a point P, and I want to find the angular momentum about P, I should do moment of mvg about P plus ig omega.